Okay. So another transition metal lunch. For the coordination compound hexamine cobalt 2 fluoride, we have these sets of things. Which one is true? So first off, we've got hexamine cobalt 2 chloride. So that first one, the coordination number is 2. How many things do we have sitting around that metal center? Very different ligands. We have hexamine and a chloride. Hexa is, in terms of numbers, 6, right? So if we've already got hexamine, there's no way coordination number could be 2, because we got 6 amines sitting around. There are Cl- ligands. What does chloride mean? Cl-, it's there. There are bidentate ligands. So those are ligands that have 2 places to bind, two available sites that they can bind. Something like ethylene diamine. Who knows what the amine ligand is? Okay. Amines are nitrogen-containing compounds, right? They're in organic chemistry, anyway, they're NH2s. So an amine in this case is actually an NH3, which is not going to be bidentate. Chloride's not bidentate; it's just one atom. The complex ion has a -1 charge, so that's the whole complex, right? It's cobalt 2, but it's chloride, and the amine is neutral. Even if it wasn't neutral, it would still end up with some crazy charge that wasn't -1, right? And we're left with this last one. There are 6 NH3 ligands. So if you know AMMINE is NH3, you can go hexamine, 6 NH3 ligands. Done. Okay? Make sense? Any questions? Yes?
Were those 2 for Leopolds?
Yes, those are for Leopolds.
Okay.
So John's going to do a couple from the Massari one right now, and then we will have open questions from the material that we will try to answer to the best of our ability.
There's a lot of writing.
I had no idea what you were thinking, but
Yeah, I remember.
I just know that it's attached to the transition.
All right. There's one last answer I need to write up here yet, too. So this is from a Massari exam regarding semiconductors and solar cells. Now, it's helpful that I'm doing this question because actually Stephen is my TA for a graduate class that I'm taking, and I have an exam on Monday about this stuff. So having me work through it with you is going to help me study for my exam too. So thanks for that. All right. So in a we have a PN junction in a solar cell. Photogenerated electrons always move from the p-type material to the n-type material. And it's asking why. All right. So let's work through this. Remember how this works? We have a, I don't know how the material was presented to you, so if this doesn't make sense, let me know and I'll try and explain it another way. Okay, so I'm going to use the board because this is full. Can you still read that okay? Okay. So if we have a semiconductor and we have a p-type semiconductor, you know, a semiconductor is often silicon, so we have a whole bunch of silicon atoms. And for a p-type semiconductor, what you do is you take out a couple of the silicons and you dope it with something that has fewer electrons than silicon. And I can't remember off the top of my head. Oh, there's a pair of people. So often you'll have gallium. So you can see silicon over there with at the 14. Something that has fewer electrons is going to be to the left. So if you dope in gallium, Ga, that'll give you a p-type semiconductor. So this is p-type. And in N-type, you're going to dope in something that has more electrons than silicon. So something like arsenic or phosphorus. Phosphorus? Yeah, phosphorus. Put in arsenic. Okay? All right. Now, question is why, when we have sunlight hitting this thing, do electrons always move from here to there, even though there's fewer electrons here than there are there? Do I have this backwards? I didn't think so. Okay. All right. So the first one says they do not. They actually move from here to there. Could be. Maybe. All right. What's the next one? Because the p-type material has a positive charge at its interface after the Fermi levels equilibrate. Okay? C, because the electric field drives the electrons from the p-type to the n-type. D, because the photogenerated holes in the valence band are moving towards the n-type and the electrons are attracted to the positively charged holes. Because the bands bend up, more negative potential in the p-type material. Okay, so there's some other words here we need to think about. Valence bands and Fermi levels and things like that, right? So you can think about when you have a big solid like this, we don't really think about it as being an orbital and a particular level where the electrons exist. The electrons exist in bands, so it's more continuous. So this is kind of like a sea of electrons here. The electrons are kind of all over the place here. They can float around all inside there. So what you get
So if you were to draw an electron level diagram, normally they look like this, right? You put your electrons in it like that. For a solid, it's more of a continuous band. And so what we have is we have a filled band and a valence band. And there's an energy gap right here. Now that energy gap is going to, if they're touching, the material is a conductor. And if they're really far apart, it's an insulator. And if they're somewhat close, it's going to be a semiconductor. So here we've got it somewhat close. And the way I've drawn it is just for pure silicon without anything doped in it. But if we add an electron, or if we dope in gallium, which way does it go? For a p-type, what's in here?
I don't know if it's relevant.
It's not really relevant. Okay. Okay. I think I'm going into this far more than I need to. All right, go for it. Go for it.
So first of all, we didn't actually get to p-n junctions when we covered this material.
Oh, really?
This is a
Okay.
perfectly fine thing to cover. So this was the valence band.
Oh, that's right. That's the valence band. That's the band. Yeah. Thank you.
So this was our conduction band, which is where the empty orbitals are. And this is our valence band, which is where the filled orbitals are. So the way to think about this problem, even though we haven't talked about p-n junctions, is to say that there is a there's a p-type material. It has a valence band and a conduction band, and it's touching with an n-type material, which has a valence band and a conduction band. Conduction band. P-type, N-type, and we've just touched them together. So the P-type had a Fermi level, which was down here close to the edge of the valence band. The N-type had a Fermi level which was close to the conduction band. This is E Fermi. And what we said in class is that the Fermi level is effectively a measure of electrochemical potential. We can think about that as just like you would think about a half-cell potential in Appendix D. So if you touch these two things together, they're physically touching, what's going to happen is that the Fermi levels are going to equilibrate. The conduction band in the N-type material has a few extra electrons in it. The valence band has a few missing electrons in the P-type material. So when you touch these together, the spontaneous reaction is electrons always move from the more negative half-cell potential, which is up. This is like Appendix D flipped upside down. The electrons move from the more negative half-cell potential to the more positive half-cell potential. So the spontaneous reaction is electrons from there into here, driven by the difference in the Fermi levels. As they're spilling out, as these electrons are spilling out of the conduction band, the Fermi level of the valence band is going up. The Fermi level of the N-type material is coming down until they're equilibrated. And this is all in the dark. We just touched two materials in the dark, and this occurred.